Great. So it is now 7 o'clock. So I will just give everybody one more minute and then we will begin. So in the chat function, welcome to those who just joined us. In the chat function, I have written my mobile phone number and my email address for Friends of Benley Viaduct. If you're having any technical problems, you can send me a quick text message or email me. I may not be able to respond if there is a lot going on in the session, but I will promise I'll do my best to give you some tech support if possible. Thank you to everybody who's arrived. Just give it another minute for those of us who have trouble signing in or logging in. Okay. Well, welcome everybody. It's 1 minute past 7, so we will give it a start. My name is Kate Crossley. I'm the manager of the charity called the Friends of Benley Viaduct, and we are so grateful that you've decided to join us for our fantastic talk this evening. I'll start with a little bit of housekeeping before we move on to Peter's main event. The Friends of Benley Viaduct are hosting this meeting to raise money for their charity and to raise awareness of the fabulous local industrial history in our area. So thank you to all of those who sent us a donation through Zoom. I'll also put a link to how you can donate at the end in case you enjoyed the talk so much that you want to send us a few more donations. We will be recording this meeting tonight, but your faces will not show on it. It will only be Peter's face that is showing, or or my face that's showing. We will talk for approximately 45 minutes. Peter will be giving you some fantastic information on Victorian Tunnelling. Then we will have a few minutes for questions. If you want to ask a question, you can put it in the chat function, which you can access down at the bottom. And there's also something called a Q&A function where I can see your questions and I'll read them out to Peter as we go. If you have any technical issues, I've put my telephone number and my email address in the chat. I may not be able to help you if there's a lot going on, but I promise I'll do my best to answer all of those emails and all of those messages. And I just want to thank you again on behalf of the Friends of Benley Viaduct. We're exceptionally proud of the work that we've been able to do to rescue and reopen and promote Benley Viaduct. And as railway and history enthusiasts, if you would like to find out more about how to support our charity in future, I'll also pop a link to that towards the end. So without further housekeeping or more messing around, I'd love to welcome Peter Harris. Many of you will know that Peter Harris is an exceptional civil and structural engineer, but he also has an MA in history and is a long-standing friend of Benley Viaduct. And his tours around the Benley Viaduct walk are not to be missed. So come and see us during spring and summer if you'd like to see it in person. So thank you very much. And we will now switch over to Peter Harris. Okay, so here you are.
Need the pointer. Right, well, hopefully we can get going now. What I was going to talk about tonight is historical tunnel construction. Basically, how tunnels were built in that period from about 1780 with the canals right through to about 1890. And the topics I'm going to cover are how they built the shafts, how they sank the shafts, how they constructed headings between the shafts and along the line of the tunnel, then how they constructed the main tunnel itself, and finally talk about some construction features. The sources I've used in putting this together are Frederick Sims' Practical Tunnelling, written in 1845 and then upgraded in the third edition 1896, and that's where most of the illustrations that I'm going to use tonight come from. I'm also going to make reference to a couple of comments by Charles Gripper in his Railway Tunnel in Heavily Ground, written in 1879, just after these tunnels were completed. And also a couple of references to Thomas Walker, who built the Severn Tunnel, its construction and difficulties, 1872 to 1887. And I'll also be using some references from the Forgotten Relics website run by my friend Graham Bickerdike. So firstly, let's have a little bit of a general overview about the line in general. The Derbyshire and Staffordshire Extension Railway, which ran from Egerton Junction through Etwall, Mickleover, into Derby Friargate, and then out again through Bredsall, West Hallam, Ilkeston, Bentley Viaduct, through Kimberley, and eventually on to Gedling and Nottingham itself. And there are 4 tunnels on the line, one at Mickleover, which we'll talk about, one at Morley, just the other side of Bredsall, Watnell Tunnel near Kimberley, and finally the big tunnel at Gedling, the Mapley Tunnel. I'm going to use those initially as illustrations for some of the things that we're going to talk about. Firstly, Morley Tunnel, very short tunnel. It's only 238 yards long. Picture on the right shows it before it was infilled. It's now completely buried, although the Greenway cycle track, which will eventually connect to Bentley Viaduct, does run over the track, over the tunnel. It's a very short tunnel, 238 yards. So you could theoretically and almost certainly drive this from the 2 ends. That would enable you to have basically 1 shift of miners to do the excavation and 1 shift of bricklayers to lay the bricks to form the tunnel, and they would alternate from one end to the other. You just have two faces, 1 at each end. So that would be a very simple tunnel to construct. Then if we look at Watnell, Watnell is slightly longer, just 288 yards. The picture on the right again shows it in its very deep rock cutting. You can see that both in the plan. This is the 1880 Ordnance Survey plan showing the rock cut in each side. And the tunnel again, sadly, has now been infilled. And again, at 288 yards, it's on the limit of the sort of thing where you'd want to build it working in from the 2 ends with just 2 faces. But the next one is the big one, Mapley Tunnel, 1,132 yards long. At that, it's the 22nd longest tunnel in Britain. There are about roughly 700 abandoned tunnels and roughly 700 tunnels still in use. So this was built with 6 shafts. In order to build a tunnel economically, once it's over about 200 to 300 yards long, you need to have more faces. Now this one had originally 6 shafts. 3 of these have been filled in and 3 of them are left open. And we can see the open ones here. If you can see where my laser pointer is, there's an air shaft. That's one of the construction shafts. That's another one, and that's another. And there were 3 others. Now, where those 3 isn't quite clear, but one, if you look around the shaft, you can see these mounds. This is the spoil which was excavated from the tunnel, which was just deposited as close as possible to the shaft. So there's a mound just there. So I suspect there was another shaft there. There's a mounded area at just behind the portal here. So I think there'll be another shaft there and possibly another one in the middle of that field. 6 shafts. So 3 of them have been filled in, 3 left open. That would enable you to have 14 faces to work from, and then you'd have in effect 7 teams of miners excavating at one end, 7 teams of bricklayers working at the other, and they would alternate from one position to another, and that would be the economic way of building a tunnel as long as this. Interestingly, the next one is Mickleover Tunnel, which is a bit odd because it's 464 yards long, which is too long to build without shafts. And yet here we see on the 1880 map, just literally 2 years after the tunnel was built, you've got the cutting at one end, the cutting at the other, and the curved tunnel. That in itself presents some engineering challenges to build a tunnel on a curve. And there are no sign of any shafts whatsoever. For a tunnel this long, I would expect at least one, possibly two. So I consulted my friend Graham Brickadike, and he came up with the newspaper report. So there was at least one shaft. We don't know where it is. I suspect it was probably in the middle. And although there's no spoil mound there to show where the waste was tipped, it may well be that the landowner who arranged for access to this probably insisted that all the waste was moved, or indeed perhaps the waste was taken away and used as part of all the works on the line. However, we do know there was at least one tunnel, one shaft. And the sad reason we know that is because on the 6th of December 1878, Thomas Smith, one of the labourers, came out of up the shaft at 6 p.m, which would be in the dark, got to the top of the shaft and ready to go home, and unfortunately he misstepped and fell down the shaft, broke both legs, broke his back, and sadly died in hospital 8 days later. One of the unfortunate problems we have with tunnelling, it is a dangerous business. And there was an inquest on his death, and they decided it was accidental death, not the sort of thing you would get with health and safety regulations nowadays. Again, there's a picture of the tunnel on the right there from Peter Kazimierczak from the Forgotten Relics website. And again, sadly, this tunnel has now been filled in, although there is a cycle track up and over the top. To illustrate how tunnels were constructed, I'm going to use a lot of illustrations from Sims's book. And this is the works at Bletchingley Tunnel in Sussex down in 1842. And there are some interesting features in this photograph. This is where one of the shafts would be, and this has got a horse gin. That horizontal drum, there are 2 horses walking around in a circle, and they're winding the rope onto that, on and off that drum, to lower the shaft, the bucket up and down the shaft. In the centre there is this timber tower, and that's a sighting tower, and we'll talk about that in a few minutes. That was used to set out the line of the tunnel. And in the foreground, there is this horse and cart with 3 enormous tree trunks on it. And again, they're timbers that are going to be used in the construction of the tunnel, and we'll be talking about them as we go along. So, as I said earlier, you could construct a tunnel from two ends. You'd have 2 working faces, one being excavated and one being bricked up. Okay for short tunnels. This is Bletchingley Tunnel, and this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 shafts. So theoretically, you'd get 26 working faces, and you'd have 13 sets of miners and 13 sets of bricklayers to make this economical. On the top there, you can see the sighting tower, and we'll look at how that works. So sighting tower usually is a timber construction around a brick or stone core for stability, and the timber structure is to keep the wind off the instrument. In the top of the tower there's an instrument called a theodolite. This one, it can rotate. It's a fixed type of theodolite. It can rotate through 180 degrees and turn over. The picture photograph there is one in the Science Museum in London. On the right-hand side, the photograph there is a stone masonry sighting tower. It's the only one of its kind that we know of in existence. This is at Bramhope Tunnel up in Yorkshire. And again, you can see the large slot in the top of the tower through which the theodolite would be rotating. So from the sighting tower, you would look firstly in one direction along the line of the tunnel, along the line of where the railway was going to be, and then you would look the other way by rotating the theodolite through 180 degrees. But then you would also be able to sight downwards intermittently to other places on the ground, and you would be able to decide exactly where the shafts needed to be in order to set the tunnel out. Sinking a shaft is a fairly complicated business. Firstly, at ground level, you'd construct a timber frame with legs. In the bottom here, you can see a plan. You've got these large timbers going across the ground, and that would enable you to hang wrought iron rods down the tunnel, down the shaft. And as you excavated down, you would put a timber crib at say 10 to 15 feet down, and then you would line the shaft with brickwork back up, and all that would be hung from this top frame. Each time you excavated down, you would put the timber crib at the bottom and build the brickwork back up, progressively getting deeper and deeper. In this photograph here, illustration here, you can see the brickwork's been completed. There's a timber crib in place, and they're excavating down the middle of the shaft to create a void. Once you've done that, you'll progressively work outwards, and you'll probably have to put props in to hold the crib back up, and you would probably build the brickwork in panels. Here they're building a brickwork panel in the centre and a brickwork panel on the right, and then progressively excavating out and putting the rest of the brickwork in, and then you've got another timber crib. You would hang that from above and keep working down to the bottom of the shaft. I've shown here how the shaft is being excavated. You've got the horse gin to carry the material out of the shaft, drop the bricks back in. This is a steam winder at Catesby Tunnel in 1897. On the right, you've got a little engine house, and on the left, you've got the actual shaft headgear with its pulley wheel over the top. They've put a temporary railway along the side, and as you can see, the ground is being built up around the headgear there. As progressively they're excavating more material, they're just literally dropping it each side and created a waste mound. This is also from Catesby in 1897. This is a little steam crane. So rather than have a horse gin or a steam winder, they've actually got a crane. And as you can see, there's two men on the crane operating it. And there's the kibble bucket that's to go down the shaft, and four of the miners on the bucket. And again, just think of the health and safety implications of that. One's sitting on the edge of the bucket, and the other one's actually standing on it. Things were quite different in those days. This is a typical illustration of a horse gin from 1845. And this sort of equipment was used at a lot of coal mines in that period for winding coal up and down the shaft at a coal mine. So it's a fairly standard piece of equipment. And very often in the early days, every shaft would have a horse gin. Later, probably 50% would have horse gins and 50% would have a steam winder and possibly steam pumps as well. But again, you can see on the shaft there's a platform on the top, and the banksman there is just guiding the rope down the shaft and probably signalling to the horse holders when to stop and get the bucket correctly at the bottom of the shaft. And in this illustration, you can see the brickwork for the shaft is progressing downwards. Most shafts at this time, construction shafts and ventilation shafts, were about 9 foot or 10 foot in diameter. Brunel, on some of his tunnels down at, say, Sapperton, used alternating 10 foot and 20 foot diameter shafts. He was quite keen on using big shafts, and certainly the Stevensons used some larger shafts, but they went out of fashion very quickly, and 9 and 10 foot was a sort of standard diameter. eventually you can only go so far down. In the bottom of this illustration, there's the little arch, and that's where the actual brick tunnel is going to be eventually. So you can't take your brick shaft all the way down at this stage. So you would stop and put a timber crib in, and then you would excavate 4 small tunnels, about 18 inches in size, very tiny tunnels that somebody's going to have to crawl into, excavate out, and put these large 15-inch timber pieces in, thread them in, push them in with a scarf joint, a central piece, and another piece the other side. And this would be a few feet above where the real tunnel is going to be. In plan, you've got 2 long sections and 2 short sections, and this temporarily supports the brickwork. After that, you would then change from a circular brick shaft into a square timber shaft and excavate that all the way down, excavate, brace, all timbered out, right down and a little bit below where the bottom of the main tunnel is going to be. And in this drawing here, you can see the outline of where the brickwork is going to be. You'll notice on this one, it's actually got a hand winder, literally, not a horse gin or a steam engine. It's literally wound by hand. And that was at Saltwood Tunnel, another one that Sims worked on for the Southern Railway. And down at the bottom here, on the line of the main tunnel, you've got a timber heading, and you're going to excavate that out, left and right, and join up all the shafts together all the way to the portals, connect the whole lot up. And in doing so, that'll enable you to confirm the line of the tunnel, particularly if it's curved. But the timber heading in the 1840s was usually quite a small affair. Once you'd got the shaft, the timber part of the shaft down to the bottom, you would use a theodolite or your sighting tower to mark on a timber frame the actual centre line of the shaft at that point. And you would hang wires down the shaft with a large plumb bob on the end. Plumb bobs would sometimes be hung into a bucket of oil or slurry in order to stabilize the plumb bobs. But once they were down there, that would give you accurately the line of where the tunnel was going to be. The miners would then excavate this timber heading with posts and boards progressively, and they would, at the face, they would hang a candle from the centre line of the timber heading, and then they would be able to sight back to the shaft, to those wires, to make sure that the line of the tunnel was correct. And this is a picture from the 1840s from Sim's book of how the miners would work. Two miners in the face. One would be excavating out and banging in the headboards ahead of himself and erecting posts to hold the timber excavation open. The other one behind him is shoveling the waste material that he's chucking out, and they're putting it in a little wagon, which would run on timber rails and taking it out to the shaft. And this small size of construction, probably 5-6 foot high, 3 or 4 foot wide, was typical of the 1840s. But one thing we do know is that progressively during the Victorian period, headings did get significantly bigger. And by the time of our tunnels, they would probably be 6 or 8 foot high and possibly 8 or 10 foot wide. So in the illustration here, we've got the shafts down, we've got the heading all the way through, and it's just a small timber tunnel. We've gone a little bit below where the main tunnel is going to be to form a sump. That helps with the drainage. And then in this illustration, with the brickwork right down to just the top of the shaft, we'll then start excavating out left and right from each shaft, and also in from the portals. So in this one with 2 shafts, we've got 6 working faces and 3 teams of miners, 3 teams of bricklayers. This is the geometry of Bletchingley and Saltwood tunnels, one on the left, one on the right. One thing that Network Rail did about 25 years ago, mistakenly, was refer to this shape of tunnel as being a parabolic tunnel. It's definitely not parabolic. I tend to refer to it as a horseshoe tunnel. And the reason why it's not parabolic is because they couldn't mathematically calculate parabolas accurately. So in actual fact, this is made up of circular curves. Round the top here in the crown, we've got a 9-foot radius, and that's its centre. Then in the haunches, this area here, we've got a 15-foot radius with a centre there and there. They have a tangent point just there. And finally, in the side walls, you've got about, I think it's a 21-foot radius. Sometimes that's larger. And again, you've got a centre there and there. So it's made up of in fact, 5 circular curves. This is quite a thick tunnel. Varies from 1'6" up to 3 foot thick, depending on the quality of the ground. And this tunnel has an invert. Well, both of them did. This invert is a curved strut made up of brickwork, and you require this in soft ground, where as well as the vertical pressure of the ground from above, you've also got horizontal pressure as well, trying to squash the tunnel from side to side. So an inverted arch like this actually braces the sides and stops them being pushed in. In this corner here, between the invert and the side wall, you've got a construction called a skew back. We'll look at that in a minute. This was a twin track tunnel, and Sims was very keen on putting a circular drain down the middle. This is quite a large drain. So having gone on about the circular curves, the problem is that that's fine for their final construction. It's fine for the temporary works that the bricklayers are going to need in order to build the walls, but the miners themselves can't use that. So on the right-hand side, we've got offsets down, vertically down in feet, down to 30 feet there. And at each one, there is a horizontal dimension. So at 1 foot down, 4 foot 8.5. And that's the dimension that the miner works to. So as he progressively works down, he actually works outwards. And it gives him the profile that he's going to excavate in order for the bricklayers to put in the correct shape. So you're going to start at the top of the crown, excavate a very tiny heading, and install 2 of those large timber tree trunks that we saw earlier, and board over the top of it and put a prop in. Once you've done that, you'll then extend to the side, put another tree trunk and another prop, and excavate further to the side, progressively making the excavation wider and wider. And here we are with a lot of the crown bars in, and tunnels getting wider, and you're getting more and more props. And that's how the miner would be working, using either a clay spade or a shovel, and progressively banging in timbers to support the sides and keep the ground stable. Pretty hard work, particularly when in this early phase at the top. Now I have to apologise for this because I haven't got a slide that shows this correctly. This is how they would actually be working away at the top and working away from the shaft. This is a few weeks later when they've actually got some of the tunnel in place, but it shows the general procedure. That you've got these large tree trunks. Now here they're standing on part of the bricked up tunnel. Initially they'd come away from the shaft, and they've excavated out and timbered all that area there. They put props in, and they've put a big sill beam in. And back here, they've got another sill and a raking prop. And they're timbering the face in this case because they're working in very soft ground. So not only they're holding the ground up above, but they're holding the face of the tunnel in place. At the bottom, you've got the timber heading which went through to establish the line of the tunnel, and that's being progressively demolished as the miners cut out the material, load it into wagons, and push it back to the material back to the shaft. So here in this illustration again, you can see they've got the shaft in place and the headings are working away, and you've still got a little sump at the bottom there to collect the drainage. And in a lot of cases, many of the shafts would have a steam pump to pump out the water. This is a two-part illustration. Firstly, it shows looking ahead to the face of where the excavation's got to. You can see basically that dotted line is the profile we're going to build. You've got all the big tree trunks supporting the ground and all the boards. And then the bottom from L to L, you've got a former. And that's been put in so the bricklayers can build the skew backs and lay the invert bricks. And then the side here from E to E, and there, you've got again a curved profile board for them to build the side walls. This is the skew back detail, and it's basically the skew back connects the brickwork in the invert to the brickwork in the side walls. And this is a brick skew back. Occasionally you get stone ones, which are quite heavy and must have been quite difficult to get in place. But basically a brick one, you would build the bottom piece and then build the invert, build the top part of the skew back, and then you would build the side wall. And these bricks were actually laid dry in a box above ground level, and they were actually cut with a saw to that profile, and same with the top part. So they came down as a kit for the bricklayers, already cut and shaped to work. This is a illustration of when the skew backs, the invert, and the arch has been built. This one is probably in quite good ground. You've not got so many big timbers supporting the roof of the ground, and you've got little brick piers that have been built in between them. And this shows the face of the heading, and then they put these 4 vertical posts in, and they've built a frame. So the bricklayers can lay the sidewalls quite easily because they're not far off vertical, so they can just lay the bricks as they go. But once you get into the haunch and the crown area, you've got to have the bricks supported. So they've got these centering frames up here, and then they've got laggings between them. That's that dark line. And basically they put a lagging in, lay some bricks, put some more laggings in, lay some more bricks overhand into the back, and progressively putting more and more laggings in and laying bricks. And you'll have, within your gang of bricklayers, you'll have one gang doing one side and one gang doing the other. They were all employed as lump labour by a man called a butty man, and he would have a team of maybe 6 or 8 bricklayers, 3 or 4 working one side, 3 or 4 working the other. Problem comes when you get to the crown right up here, because progressively you're getting less and less space. This is a similar illustration of a tunnel in very, very soft ground, and you've got the whole thing lined out with the big pieces of timber. Now, I should have said earlier about how far we're going to work. They refer to working a face in lengths. That's how far the miners are going to excavate before the bricklayers go in. Now, that length is variable. It depends on how good the ground actually is. And sort of typical values are 8 foot up to about 17 or 18 feet. If the ground is good, you'll have a long length. And if the ground's not so good, you'll have a short one. At Highbull Road Tunnel in Mickleover, that was all done in 8 foot lengths because it was excavated through sand. So it was difficult to support. And this is where Gripper's comment about heavy ground comes in. They're not saying that in our terms now, that piece of ground isn't any heavier than any other, but we refer to it as either loose ground or good ground or semi-rock. But in those days, working in sand and loose clays, they would refer to that as being heavy ground, and the actual rate of advance would be very much shorter. Again, this is the centering in place. And this is a typical centering detail. They're timber frames, they're pre-made. You would need 3 or 4 per length of tunnel you are going to build. And they all come as a kit, and they're bolted together on site. And you you put them in, build the brickwork. And when the brickwork is set, you take them out and move them on to the next piece of work, take them back up the shaft, move them to somewhere else. This is a frame in Dovehole's tunnel in 1860, and in some cases this has been said, oh, this is the centering for the tunnel. Well, it's not actually. It's a temporary frame put in as centering for a repair to the tunnel. This was a twin track tunnel. In order to repair the brickwork at some dates in the 1860s, they've put a single track down the middle, and this frame was to support the brickwork and the new replacement brickwork. Different parts of the country had different traditions. In the south and in a lot of tunnels, the bricks are laid as 4-inch rings individually. In the side walls, you'd be able to bond them because they're not far off vertical. Once you get round the arches, you have to do them in single rings. But in the north of England, particularly around the Manchester area, there was a tradition of building 9-inch rings rather than 4-inch, and having them bonded and having separate 9-inch rings. And here you can see at Clifton Hall Tunnel, built in 1850, 3 9-inch rings of brickwork, and intermittently there are cross-bonded areas called vertical bonding. And there's also here, you can see the timbers that form the excavation are left in place, and there's little brick piers in there, and it says rubble filling. And of course, this is where the big round timbers would be. And they've been dragged forward. I'll talk about that in a minute. I don't believe that at Clifton Hall, any of this rubble packing was got in place. I think it would be extremely difficult to do. Sadly, in 1953, one of the infilled shafts and the void above it, around it, collapsed. And in the 1940s, they built a housing estate over the top, and 3 houses collapsed into the tunnel and 5 people were killed. But back to the brickwork, the final part is actually closing the crown. So you're still going to have those big timbers in there, and this width that you've got to fill with brickwork is getting smaller and smaller. So you can't have 3 or 4 bricklayers working on each side. It becomes a one-man job, and he basically has some little cross timbers to put in to fill that void. And he's got to lay the bricks above himself overhand, which is a very tedious task, a lot of hard work. So he gets paid more than the other bricklayers laying the sidewalls and the arches. So in this illustration here, you've still got the timber square shaft in place, and you're building the brickwork and excavation to the left, and you've excavated to the right. Eventually, you get the brickwork in both sides. You can see the centering frames there and there. Eventually, you can take those out and fill in this shaft length, the bit in the middle. There you've got the centering frames in the middle, and you've finally formed the brickwork at the bottom of the shaft. And this is called a shaft eye, and we'll talk a little bit more about that later. But you can see the form of the excavation, and then you're going to progress left and right from there. Again, you're going to do a small top heading, and you're going to drag those timbers forwards. You'll be using pinch bars to catch into those timber tree trunks, and you'll drag them into the top of your new excavation progressively, one after the other. And that's pretty hard and dangerous work. That's the illustration we used before. You're working away from the shaft, progressively doing the top, doing the middle, putting raking props in, and those props notch into the brick invert there.
Just checking.
Yeah. Right. Yep. You want me to answer those now?
No, it's just checking there've been no issues with technology.
Okay, we're just looking at making sure we've actually got some questions coming in on the chat. At Highbull Road, when we did the reconstruction there, we actually excavated the track out, and we found these notches in the bottom of the invert there. And here it shows as if the notch goes into the brickwork and doesn't go all the way through. At Highbull Road, we found that the notches to the struts went all the way through, and they'd never been filled in with brickwork. They were still full of rubble. So eventually you get the brickwork completed and you move on to the next section progressively, working away from the shafts. From about the 1850s, 1860s, and certainly later on, they moved away from working from the shafts. I think this was possibly as a result of a collapse at Watford Tunnel. And they went for breakups instead. So rather than excavate away from the shaft, they would leave that material in place, and they would go along the timber adit, and they would form a breakup and work out from there. And this actually is another way of getting even more faces to work. And this was used on the Severn Tunnel, and this is from Walker's paper, and it shows how he built a breakup. So that is a timber heading there that goes all the way through. And as you can see from the 1870s, it's much larger than the little ones used earlier. And from that timber heading, they would form an inclined tunnel and a horizontal tunnel right at the top. Then they would excavate backwards on themselves, and they would bring the big timbers up through that into place to hold the top of the tunnel up. And then they would work left and right as before, progressively putting more timbers in and supporting the ground until eventually they could form the whole profile. And the use of a breakup did enable them to build tunnels somewhat faster. Eventually, we've got the tunnel completed. We've got the shafts all bricked up. We've got the brick lining all the way through, and we're going to build the portals and head walls at the ends. I've mainly been talking about soft ground, from basically sands and clays and soft rock and mudstones, that sort of thing we get around here. This is a compressed air rock drill used at the San Gotthard Tunnel in 1875. And that's very, very similar to the one used by Captain Beaumont at Queensbury Tunnel near Bradford, one of my favourite tunnels, and quite an interesting tunnel, and has a lot of controversy over it at the moment. And that was used that was one of the first rock tunnels in England, using technology developed in the mining industry. And basically this is a rail mounted compressed air rock drill with 4 rock drills on the front, and they would drill into the rock, put in a charge of black powder, or later they would use tonite or dynamite, and they would actually blow the face and excavate the material. And this is possibly used at Watnall and that rock excavation there. Of course, if you're doing a rock excavation, it's a bit hit and miss with black powder or other explosives, and you tend to get a lot of overbreak. Now, it's not easy to see it, but that curved piece of brickwork there, that's actually the outside of the tunnel lining. The tunnel is below here. That's the crown of the tunnel. And you've got these voids above, and rather than fill the voids and pack them as they perhaps should have done, they've just built these little brick piers to hold the rock up. Very hit and miss. And there's certainly evidence that occurs at Queensbury Tunnel. The head walls, we'll talk a little bit about those details. These are wing walls done in the 1830s and 40s, and they're almost perpendicular to the track. Very typical down south. Nice portal with voussoirs and a slightly Greek sort of facing. But the wing walls themselves, although slightly curved, are basically almost perpendicular to the track. And there's been quite a few of these fail over the years, as the ground pressure tends to push them outwards. And that's a typical section through a head wall. You've got the ornate brickwork there, the solid brickwork, and the invert roof of the tunnel, and the slope of the ground above, and the drain at the top there. We've had a lot of problems with these drains getting full of debris over 100 years and then leaking into the tunnel. This is from CEng down south, showing how they would actually excavate out the portal and timber it out before the brickwork is there. They've brought the brickwork for the actual main tunnel through, and then they'll build the head wall inside there. And this is going to have nice wing walls parallel to the track, which is a much better structural solution. I'm showing this one because it's one of Brunel's, and it's typical of the Great Western, a much wider tunnel and a very ornate ragged stone voussoirs, and really nice curved wing walls, quite complicated to construct, and they're stepped up the slope. But what's interesting here is that this inner line is the actual tunnel. And basically, at the portal, they've created a bell mouth. They've raised the tunnel crown up and created a larger void there. And I'll show this in the next slide. So on the right, that's the main standard tunnel profile, 20 foot or so, 20'6" high. And that's the tunnel brickwork. And they've created this funnel-shaped bell mouth at the portal. Now, at the time Brunel was building this, the trains were doing 30 to 40, maybe even 50 miles per hour. But it shows that they were concerned about the change in air pressure inside the carriages as they went through. And they thought there would be a shock of pressure as one of their trains entered the tunnel. Obviously, this was a complete fallacy. At those sort of speeds, it didn't happen at all. But interestingly now, as we're building modern tunnels, we are creating bell mouths for the same thing. But of course, our trains are traveling at 120 or 200 miles per hour, and we really do get a shock wave when a train bursts into the tunnel, or also in the opposite direction as well, sucking air out of the tunnel. So this was a feature that Brunel used misguidedly at the time. And this is a sort of typical pepper pot tower you get on the shafts that are left open for ventilation, and quite a nice tower, slightly tapered, cornice around it, and a cast and wrought iron grill over the top of it. And you still see some of these. There are a few still left in existence up and down the country. Very often they got taken off, sometimes because they corroded and replaced, and sometimes removed by vandals on abandoned tunnels. I talked about the cast iron, the eye, where the shaft and the main tunnel intersect. And this is a cast iron curb or shaft eye used by Stephenson's. So in the middle, you've got a circular in plan. Above and below, you've got the elevations, and to the side, you've got the elevation looking left and right. So these were 4-part cast iron castings made in a forge and then delivered to site in 4 pieces. Lifted into the top of the tunnel and then bolted into place. Now, it's a typical Stephenson detail from the 1830s, 1840s. Sevenoaks Tunnel has quite a few. Claycross has them exclusively. Summit Tunnel. Shildon was one of the first ones. I've been in there, and the casting quality was atrocious. And Watford Fast. They must have been extremely difficult to get into place, to lift them up and get them into and build the brickwork around them. And I suspect that when they had the big collapse at Watford Fast, one of the shafts actually collapsed. And that was when they were trying to get this curb into place. This is a more northern England detail. It's a very nice stone masonry shaft eye with very nice voussoirs reminiscent of a bridge type detail. And again, you can see these are the way they're toothed into the brickwork. They're in two layers, and then there's the brickwork shaft above that. That feature there is a garland drain to try and catch water that might be coming down the shaft, rainwater or groundwater leaking into it. That's quite a nice detail, very, very common in Yorkshire and Lancashire and further north. But of course, the simplest way is to do it in brickwork. This is a very nice brick shaft eye at Brodsworth Tunnel. Brodsworth's an abandoned tunnel, and we can look up the shaft and we can see a roof over there. There's some joists and concrete slabs, and this is because it's an abandoned tunnel and the little tower has been demolished. And the top of the shaft has been sealed. But one of the interesting features about that is this detail around the edge of the shaft eye. There's a very nice curved bullnose brick. And one of the reasons for that, or not even an architectural reason at all, is just that when they were winding things up and down the shaft, if you had a sharp brick edge and your winding rope caught on it, it would fray the rope. So they put a rounded bullnose brick around that edge. I think a nice detail. So almost in conclusion now, looking at Mapley Tunnel, this is the unclosed portal at Mapley. The other end is buried. As I said, it was the longest tunnel built on the line. You can't get access in there now. And 3 of the shafts were filled and 3 of them were left open. And I thought you might like to see this in conclusion. This is one of the open shafts left open for ventilation. And when the tunnel was abandoned, all the local skip tippers came and chucked all their rubbish. There's lots of metalwork and all sorts of stuff down there. And that pile of rubbish is actually standing inside the shaft, dangerously unsafe. But anyway, finally, that's the end of the talk. And thank you. Any questions?
Hi, everybody. Thank you so much for being patient with our problems with technology earlier. Many of you have discovered that the chat function's not working, but the Q&A function is working. So I'm just going to get some of these questions up for Peter, and he'll be able to read who's given us the question and answer those questions very quickly. If you do have any other questions, you can please put them in the Q&A talk. All right, so thank you so much to John Longren, who just mentioned that there was no need to apologise for the beginning. Well, thank you for being so kind. He's also mentioned something that I think Peter can mention.
So John Longren, very good talk. No need for the breakup partly answers my question on how the shaft brickwork didn't collapse. Well, as I showed in one of the illustrations, they would take the square timber work down to the bottom, excavate to the left and fill that with brickwork, excavate to the right and fill that with brickwork. And having had 2 brickwork sections of tunnel in place, they would then take out that square work and put in that frame and build the shaft eye. So it's a sequential thing. But certainly I think at Watford Fast, when the collapse occurred there, it appears to have occurred when they were trying to actually finish that section, and that's called the shaft length. In Haywards Heath and Clayton tunnels is on the Brighton line. That's not Clayton Tunnel in Bradford. On the Brighton main line, the tunnels are corbelled, which seems a lot of extra work to me. Any idea why? I'm not quite sure what you mean by the tunnels are corbelled. If you could send me a sketch of that. I've not been in Haywards Heath and Clayton on the Brighton line. Yeah, I'm not quite sure what that one is. Anonymous attendee, how did they check the depth of the construction shafts needed to ensure that the floor ran to the required levels and gradients? Well, they would have the shafts, and the surveyors would set out the line of the shafts, and they would know from the surveying of the level of the top of the shaft how deep they needed to be, roughly. One of the purposes of putting through the timber heading is that the timber headings then connect all the shafts, and that gives you your ability to do the final check of the line of the tunnel, whether it's in a straight line or a curve, and also to check the level, and it gave you some sort of assurance of that. I must admit, Bradway Tunnel on the line between Derby and Sheffield did have one whole length that was something like about 300 mil out of line, and we never could work out why that one was done wrong. Mick Cresswell, I'm sure there is a sighting tower made from stone at Milford. Now, that's very true. It looks like a sighting tower. It's not. That's not a sighting tower. That's actually a signal tower. At the time when Milford was built, there was no electronic signalling or mechanical signalling. So they had a man in the tower on top of Milford Tunnel with a flag, and he would know when trains were coming, and he would display flags so that the trains coming south would know that they could actually travel through the tunnel. Yes, I've actually been up to that. It's quite a nice structure. Matt Davis, when did sighting towers first appear? Could they have been used for Glenfield? Almost certainly for Glenfield Tunnel. They were used for the canal tunnels in the 1780s and 1790s. So yes, there would have been a sighting tower somewhere, and sometimes there would be more than one. A Butterley Tunnel on the Cromford Canal had 37 shafts at 70-foot intervals in order to build that on time. And one of the stories we do have is that progressively through the Victorian period, the number of shafts gets less and less, the headings get bigger, and the length distance between shafts gets larger. But yes, almost certainly. Right, Lucy Grace, who has a map register of all the voids? I know the Coal Authority has mines and shafts. Do they have tunnels and associated shafts too? It would depend on who built the tunnel and the shaft. Network Rail has a very, very good database of all the 700 tunnels that they have in use. They started a process about 25 years ago, producing a tunnel management strategy for each of their tunnels. And in doing that, they commissioned consultants, of which my company at the time was one, and we did over 200 studies for Network Rail. And we were looking at the archives down in the National Archives in London, looking at the archives of the actual tunneling, the railway construction companies, to try and find out what drawings there were of the tunnels and whether they showed the shafts. The one I showed you for Bletchingley with its 12 shafts is an archive drawing from that period. For more than half the tunnels we studied, we were able to find the original archive drawings. Sometimes we did searches in newspapers, which referred to the shafts being built. Certainly for Milford it does. And in some cases, we've had to say, well, like at Mapley, there were originally 6 construction shafts. Where are the other 3? Sometimes the archive drawings would show them, sometimes they wouldn't exist. And over the last 20 years, Network Rail have done a very extensive drilling job to try and locate the hidden shafts, the ones that have been filled in that you can't see from the inside. So Network Rail has a very good archive. The 700 abandoned tunnels don't have any register like that. British Rail Property Board, as it was, the Highways Agency it is now, they commissioned a series of studies like Network Rail, but not to the same level of detail, to try and find out where their shafts were. Where would I find information on the collapse of a tunnel in Southampton in the 1840s? Contractor Peto from Valencia, Spain. I would think the National Archives in London would be the first place. I'm not sure which tunnel in Southampton you're thinking of. The railway tunnel there, I think, had a collapse. If it's the still running tunnel, Network Rail would have in their tunnel management strategy, they would have the records there. Otherwise, National Archives is variable. The engineer for that was Veitch. I do know that, Lieutenant, is it Captain Veitch? It's got a very strange portal if it's the running railway tunnel. Where are we now? Okay. That was Milford when we talked about that one. North Yorkshire, on the North Yorkshire coast, we have two tunnels, Sands End and Deep Grove and Kettle, which have horizontal offshoots going out to the cliff face. Yes, the adits, and yes, the spoil will be tipped to the sea. That also happens. Which tunnel is it? One parallel to the River Avon. Clifton Down tunnel has a side. It has shafts and it has a side adit. Graham, just for my information, Stevenson type cast iron curves were used at the bottom of at least one shaft in Mapley Tunnel. Well, thanks for that, Graham. I haven't had a chance to research that, but you've obviously got a lot more information than I have. Site and tower remaining on the Quarry Tunnel in Surrey. That's not one I'm familiar with, but yeah, there are a few still around. Bramhope, yes, one has been demolished. The one I showed the photograph is the remaining one. Yeah. Mick Cresswell. Thank you very much, Mick. I wonder who the house builders applied to before constructing their new estates. As I understand it, the ones at Clifton Hall that collapsed, they were actually local authority housing estates built in the 1940s, in the post-war period. So it would be the local authority who would they have applied to anybody. I do know that some tunnels in Swadlincote, near Burton-on-Trent, a very small developer there did approach Network Rail about one of their tunnels there, and all his houses were built on reinforced concrete rafts, and the pressure on the tunnel was calculated to see that it didn't significantly affect the tunnel. Okay, well, thank you very much for all that. If you've got any other questions, then please drop us an email and we'll do our best to answer them.
Thanks so much, Peter. I'll just do the final housekeeping, and thank you so much for the talk. Hi, everyone. Thank you so much for sticking with us, and I'm sure you'll agree it was absolutely worth it. Peter's talk was, as always, fantastic.